Have you ever dreamed of exploring the farthest reaches of the universe in the blink of an eye? For generations, the notion of traveling beyond the speed of light has captivated human imagination, serving as a cornerstone of science fiction classics like Star Trek and Star Wars. Yet, what if this seemingly impossible feat wasn't just fantasy? The speed of light, clocking in at about 186,000 miles per second, stands as an unbreakable barrier in our universe, according to Albert Einstein's theory of special relativity. Nothing with mass can accelerate to or beyond this cosmic speed limit without requiring infinite energy. This fundamental rule has long confined humanity to sluggish journeys across the stars. Trips to even our nearest stellar neighbors, like Proxima Centauri at 4.2 light-years away, would take thousands of years with current technology. But science fiction writers have never let physics stand in the way of a good story. As early as 1931, author John W. Campbell introduced the concept of a space warp in his novel Islands of Space, where ships could bend space to leap vast distances instantaneously. This idea exploded in popularity with franchises like Star Trek, where the USS Enterprise zips across galaxies at warp speed, powered by a fictional warp drive that manipulates spacetime. In Star Wars, hyperdrive achieves similar feats, allowing characters to jump into hyperspace for faster-than-light travel. These narratives didn't just entertain. They inspired real scientists to ponder, could we bend the rules of physics without breaking them? Enter Mexican physicist Miguel Alcubierre, who in 1994 proposed a theoretical framework that turned sci-fi into potential science. Drawing from Einstein's general relativity, which describes gravity as the curvature of spacetime, Alcubierre envisioned a warp bubble around a spacecraft. Inside this bubble, the ship remains stationary relative to its local space, but the bubble itself warps the fabric of the universe, contracting space ahead and expanding it behind. This allows the vessel to effectively surf a wave of spacetime, covering immense distances in short times without ever exceeding light speed locally. It's a clever loophole. The ship doesn't move faster than light, but space does the moving for it. Alcubierre's idea wasn't born in a vacuum. It built on earlier work by physicists like Kip Thorne, whose research on wormholes, hypothetical tunnels through spacetime, explored time travel and FTL possibilities. Wormholes, featured in films like Interstellar, remain purely speculative and unstable in theory, requiring exotic matter to stay open. In contrast, the Alcubierre drive leverages established relativity principles, making it more grounded. Yet, it still demands negative energy density, a form of exotic energy that exerts anti-gravity effects, pushing space apart rather than pulling it together. This blend of fiction and fact makes the warp drive concept so compelling. In Star Trek, warp factors quantify the drive's power. Warp 1 breaks the light barrier. Warp 2 multiplies speed exponentially, roughly 10 times light speed in later canon. And higher factors enable galaxy-spanning voyages. The show's warp core, a reactor annihilating matter and antimatter for energy, mirrors real nuclear concepts, but scales them to fantastical levels. Such depictions have fueled public interest, leading to real-world discussions at conferences and in journals. Beyond entertainment, the allure of FTL travel addresses humanity's deepest exploratory urges. Our solar system is vast, but the galaxy is mind-bogglingly larger, 100,000 light-years across, with billions of potentially habitable planets. Conventional propulsion, like chemical rockets or even advanced ion drives, tops out at fractions of light speed. Projects like Breakthrough Starshot aim for 20% of light speed using laser sails, but even that would take decades to reach Alpha Centauri. Warp drives promise to shatter these limits, enabling interstellar colonization, resource gathering from distant asteroids, or contact with extraterrestrial life. Of course, this dream isn't without skeptics. Early critics dismissed Alcubierre's paper as mathematical curiosity, but recent advancements, such as refined models reducing energy needs, have reignited debate. In 2021, physicist Eric Lentz proposed a warp drive using positive energy alone, challenging the negative energy dogma. By 2025, over a dozen new warp models, as discussed in propulsion forums, suggest engineering might one day catch up to theory. In essence, the warp drive represents humanity's defiance of cosmic isolation. From Campbell's Pulp Fiction to Alcubierre's equations, it embodies the synergy of creativity and science. As we delve deeper, we'll uncover how this bubble of warped space-time might actually function, and why it's more than just a plot device. Imagine stepping aboard a sleek starship, the hum of advanced engines vibrating through the hull as you prepare to leap across the galaxy. No thrusters blasting flames into the void, just a subtle ripple in the fabric of reality, propelling you faster than light itself. This isn't the opening scene of a blockbuster. It's the promise of the Alcubierre warp drive, a concept that's as mind-bending as it is mathematically elegant. But how does this theoretical marvel actually work? Let's dive into the nuts and bolts, peeling back the layers of physics to reveal why it's captivating scientists and dreamers alike in 2025. At its core, the Alcubierre drive exploits Einstein's general theory of relativity, which revolutionized our understanding of gravity, not as a force, but as the curvature of spacetime, a four-dimensional tapestry where massive objects like stars and planets create dips and warps. Think of spacetime as a trampoline. Drop a bowling ball in the center, and it creates a curve that pulls nearby marbles toward it. Alcubierre's genius was to flip this on its head. Instead of letting gravity dictate the path, why not engineer the warp ourselves? The mechanics are deceptively simple, yet profoundly clever. The drive creates a warp bubble around the spacecraft, a localized region where space-time is manipulated. In front of the bubble, space contracts, pulling distant points closer, like accordion folds compressing. Behind it, space expands, pushing the origin farther away. The ship itself, It sits serenely inside the bubble, experiencing no acceleration or motion relative to its immediate surroundings. It's like being on a cosmic conveyor belt. The destination rushes toward you while you sip coffee in zero-G comfort. To visualize this, picture surfing a massive wave in the ocean. The surfer doesn't propel themselves faster than the water. They ride the wave's momentum. Similarly, the Alcubierre drive lets the ship surf a wave of spacetime, achieving apparent faster-than-light speeds without violating relativity's sacred rule. No object with mass can hit or exceed light speed in flat spacetime. As Alcubierre noted in his 1994 paper, the bubble could theoretically move at arbitrary speeds, limited only by the energy input. Recent simulations using tools like Warp Factory, an open-source toolkit from applied physics, have modeled these bubbles in stunning detail, showing how they might form stable configurations. But let's get geeky with the comparisons to fiction. In Star Trek, the warp drive's warp factors scale exponentially. Warp 1 equals light speed, Warp 2 around 10 times that, depending on the canon, and Warp 9.975 a blistering 1900 times faster. The Enterprise's warp core annihilates matter and antimatter to generate plasma for the nacelles, which create the field. Alcubierre's real version echoes this. It requires a ring of exotic matter, or negative energy density, to sustain the bubble. Positive mass curves spacetime inward. Attraction. But negative energy would curve it outward. Repulsion, enabling the contraction-expansion dynamic. Here's where the excitement ramps up with 2025 updates. Early critiques hammered the drive for needing Jupiter-sized masses of negative energy, which doesn't exist in nature. But breakthroughs are changing the game. In August, a team led by researchers at Applied Physics announced the first fully physical warp drive model that sidesteps negative energy entirely, using classical positive energy sources like plasma or electromagnetic fields. This constant velocity subluminal warp drive operates below light speed but paves the way for FTL variants. Meanwhile, other innovations abound. A September report from Alt Propulsion detailed over a dozen new warp models, including the Davis drive, which blends hypersonic plasma with warp fields for potential atmospheric use. And in October, National Geographic highlighted how these advancements could make interstellar hops feasible within decades, not centuries. Physicists are even toying with electromagnetic manipulations to induce space-time curvature, as outlined in a recent SCIRP journal paper, potentially reducing energy needs by orders of magnitude. Of course, the math isn't for the faint-hearted. Alcubierre's metric tweaks Einstein's field equations, where the stress-energy tensor dictates curvature. But don't sweat the symbols. The takeaway is that these equations hold up under scrutiny, even as quantum gravity theories loom. This blend of hardcore science and sci-fi flair makes the Alcubierre drive irresistible. It's not just about speed, it's about redefining our place in the cosmos. As we push these mechanics further, who knows what horizons we'll unlock as we hurtle toward the tantalizing horizon of faster-than-light travel. The Alcubierre warp drive stands as a beacon of human ingenuity, yet It's shrouded in a nebula of daunting obstacles and heated debates. While the mechanics paint a picture of cosmic surfing across the stars, the road to realization is riddled with scientific potholes that could derail the entire enterprise. In this final installment, we'll unpack the formidable challenges, dissect the controversies swirling in physics circles, and gaze into the crystal ball of future prospects. First, let's confront the elephant, or rather the Jupiter-sized behemoth in the room. Energy requirements. The original Alcubierre model demands an astronomical amount of energy to form and sustain the warp bubble, equivalent to converting the mass of an entire gas giant, like Jupiter, into pure energy via E equals mc squared. That's not just impractical, it's currently impossible with our technology. Even optimistic tweaks, like those from physicist Harold Sonny White in the 2010s, only reduced it to the mass of a small asteroid. Still, far beyond fusion reactors or antimatter drives. A March 2025 phys.org article highlights how the drive violates key energy conditions in general relativity, such as the strong energy condition, which prohibits the kind of negative pressure needed for expansion. Without exotic matter exhibiting negative energy density, the bubble collapses into fantasy. This leads straight into one of the biggest controversies: the existence and stability of negative energy. In quantum mechanics, phenomena like the Casimir effect produce tiny amounts of negative energy between metal plates. But scaling it up for a warp drive? Skeptics, including renowned physicist Sabine Hossenfelder, argue it's a pipe dream that flirts with violating fundamental laws. A 2025 RxIve paper explores new solutions to the Einstein field equations for Alcubierre metrics. But even these admit the need for exotic configurations that might not hold up under quantum gravity scrutiny. Critics point out that harvesting or stabilizing such energy could unleash Hawking radiation at the bubble's edges, potentially frying anything in its path, like a cosmic microwave oven on steroids. Then there's the risk of bubble instability. A sudden collapse could warp spacetime so violently that the ship and crew end up as a singularity snack. Causality paradoxes add fuel to the fire. If you can zip faster than light, you might create closed time-like curves, essentially time loops, that enable backward time travel. Imagine sending a message to your past self to prevent the trip. Hello, grandfather paradox. This isn't just philosophical musing. It's a core controversy in relativity. The Alcubierre drive, while locally respecting light speed, globally allows superluminal signaling, which many physicists see as a deal-breaker. Discussions on forums like Physics Stack Exchange rage on, with some proposing chronology protection mechanisms to forbid such setups, but no consensus exists. Overstated claims in pop science amplify the debate. NASA's EagleWorks lab dabbled in warp experiments years ago, but reports of active development often exaggerate fringe efforts. The U.S. Defense Intelligence Agency's 2018 exploration of FTL methods, including warp drives, was more speculative than serious engineering. A July 2025 article from the Brighter Side News suggests real warp drives could emerge in the next century, but it's based on optimistic interpretations of theoretical papers. Ethically, there's the sterilization issue. The drive might annihilate planets or stars in its wake due to accumulated particles at the bubble's front, turning interstellar travel into unwitting genocide. Yet, amid the storm clouds, glimmers of hope emerge. 2025 has been a banner year for warp research. In June, propulsion expert Daniel Davis introduced the Davis drive, blending hypersonic plasma with warp fields for potential subluminal and even atmospheric applications. Think warp-assisted hypersonic jets before starships. An August Popular Mechanics piece announced a fully physical warp model from Applied Physics, building on their Warp Factory toolkit, which lets researchers simulate drives without negative energy in some cases. This open-source tool has democratized warp studies, fostering over a dozen new concepts, as detailed in a June Alt Propulsion report, including positive energy variants that sidestep exotic matter. Looking ahead, collaborations between academia, NASA, and private firms like SpaceX could accelerate progress. Quantum computing might simulate warp metrics at unprecedented scales, while breakthroughs in metamaterials could mimic negative energy effects. If we crack fusion or antimatter production, energy hurdles shrink. By 2100, as some researchers predict, warp drives might evolve from theory to prototype, unlocking the galaxy for colonization and discovery. In the end, the Alcubierre drive embodies the thrill of science, pushing boundaries despite the odds. Whether it leads to star-hopping adventures or just deeper insights into the universe, the pursuit itself warps our understanding of what's possible. As Star Trek's Captain Picard might say, "Make it so."